Hello friends, you are welcome to my YouTube channel at Jamb41. In my previous video lesson, I taught you how you can carry out analysis on salts in order to determine the cation and or anion present in that given salt sample. In this video lesson, I am going to direct my attention to another part of chemistry practical, volumetric analysis. Volumetric analysis is also referred to as titration. Our aim in this part of chemistry is to determine the concentrations, of acid or bases used in a process known as neutralization. We can obtain the molar concentration, also known as molarity or concentration in mole per dm cube. We can also obtain the mass concentration, also known as concentration in grams per dm cube. This reaction, which is essentially the chemical reaction between acid and base, is known as neutralization reaction. And usually the products are salt and water, in aqueous form anyway. In dealing with this aspect of chemistry practical, we make use of apparatus like the burette. You can see my burette here clamped already with the Redox stand. Okay, so I'm going to lift it a bit for you. So you take a look, alright, with the rubber band and the clip. Here, of course, we are going to place our conical flask that will contain the base, alright, the base which, of course, we are going to titrate the acid against. The acid is meant to be, and of course, is going to be in the burette. The burette is 50 milliliter. That's 50 centimeter cube volume burette. And of course, very important is our pipette. All right, this is 25 ml pipette, 25 cubic centimeter pipette, because we're going to use this to get the quantity of base that we require, all right, for the titration. This will mean that we have to suck, all right? We'll put this end of the pipette into the base, and then we're going to suck 25 milliliter, also 25 centimeter cube volume of the base, something like this, all right? Okay, so of course we need our acid and our base for this reaction, which, like I said, the acid is going to be in the burette, and then the base is going to be in our conical flask. That is the one we are going to pipette, 25 centimeter cube portion of the base. So essentially, this is much of the apparatus and, of course, the solutions that we need for titration experiments. I've mentioned acid and base as the solutions we need. Of course, our indicator, okay, depending on the particular reagents, acid and base you use, may require a specific indicator. Of course, that is to help us actually determine the end point of the neutralization reaction. Indicators that are mostly used: phenolphthalein, we have methyl orange, of course we have the bromocresol, all right, and the list of them. Well, in this titration experiment, we are actually going to use potassium tetraozomanganate 7 solution and, of course, ammonium iron 2 sulfate, a hydrated crystal. Although titration has some other aspect of it where you deal with things like the percentage purity of a substance, you talk about, okay, carry out the neutralization reaction, just calculate the molar concentration and mass concentration. There is this other aspect of titration, redox titration, that is reduction and oxidation reaction titration. And that is actually the part of titration that this video lesson will be based on. Okay? The solutions we're going to use are ammonium iron 2 sulfate crystal, hydrated form of it. Our aim would be to determine, of course, the number of moles of water of crystallization in this ammonium iron 2 sulfate. And then, of course, our potassium tetraozomanganate 7, otherwise simply called potassium manganate 7. All right, this will contain an acid, because, of course, we are going to acidify that potassium permanganate with tetrasulfate 6. And so this potassium permanganate would be in the burette. That is our titrant. That is our titrant because we would have a known concentration value of it. And then the iron 2 sulfate, that is our ammonium iron 2 sulfate hydrated crystal, is going to serve as our base in this case. We are going to call it the analyte because it is that guy. Are you following? That is ammonium iron 2 sulfate. It is the concentration of that solution that we seek to obtain. Now, like I mentioned, this is going to be a redox titration experiment. The experiment is going to be carried out, and of course, table of value will be displayed. I'm sorry, I'm not going to display the experiment in this video lesson. Subsequently, I'm going to carry you through on how to carry out the experiment, okay, and with the solutions shown to you. But specifically, the focus of this video lesson will be on how to carry out analysis, calculations on these solutions during redox titration. Alright friends, if you are yet to subscribe to my YouTube channel, please kindly do so. Turn on the notification bell as well too after subscribing, and so that you personalize your subscription. Anytime I upload any new content, you will be personally notified. You see, this experiment is going to be an interesting one because I'm going to explain clearly how you can carry out half cell reaction equation balancing, okay, especially when you deal with the concept of the charges, the oxidation number of the major components that are reacting in the given solution. All right, and so I'm set now to go carry out the titration experiment and display, of course, the table of values. I want to say this, please, because it's going to be part of the instructions on what we need to do based on the readings I'm going to get, all right, the volume of the potassium permanganate that is going to be used for this reaction. When the table of values is displayed, part of what you are going to do is to complete the table of value. I'm not going to show you the complete table as regard what was obtained. I'll give you some of them. Are you following? Some values that I got. And then, of course, I will leave some gaps for you to fill that gap. So you have to copy and complete the table. All right? Okay, so let's move on. I'm going right away to carry out the experiment. And of course, the table of values will be displayed. Alright guys, you are welcome back. Now the redox titration experiment has been carried out and the various volumes of the titrant, that is volumes of potassium manganate 7 used in the course of the experiment, have been obtained. Alright, now I am going to display the table of readings, that is for the volume of the titrant in the burette used. But now, I'm not going to show you the full table of value, okay, for the volume of potassium manganate 7 that I used in carrying out the experiment. I would show some and then leave some gaps for you to fill. The reason being that, you know, when a student sits for an experiment, titration experiment, let us assume that it is alternative to practical. It's possible for an examiner to decide to give you an incomplete table of values for the volume of the acid used, in our case, the volume of potassium manganate 7. And then you will be asked to copy and complete the table. So I would like us to do something like that also, so that you get used to how to obtain, values that are missing from the table. So please watch the screen as I display the table of values obtained from this redox titration experiment. Please watch. You will observe from the table of readings obtained that the experiment was carried out 3 times. The first titration, second titration, and third titration. We obtained the final volumes of the titrants. That's the final volumes of the potassium manganate 7 that was used, the initial volume, and of course the actual volume of potassium manganate 7 used to neutralize the ammonium iron 2 sulfate crystals. During the first titration, the final volume of potassium manganate 7 obtained was 11.50, as you can see displaying on the screen. The initial volume at the time was 0.00. Now you are expected to complete the actual volume of potassium manganate 7 used during the first titration. And that is why you see the gap there for actual volume of the potassium manganate 7 used. So you are to obtain it. We're going to find out how we get that. Then for the second titration, you will observe that the final volume of potassium manganate 7 used was 22.60. Now, I decided not to give you the initial volume of potassium manganate 7 that was used in the second titration. Then, the actual volume of potassium manganate 7 used during the second titration was 11.10, as you can see displaying on the screen. So what are you expected to do? Get the value that should fill the gap for the initial volume of potassium manganate 7 used during the second titration. Then finally, in the third titration, the final volume of potassium manganate 7 was not given there. So you have to fill in the gap there. Determine the final volume of the titrant used in the third titration. At the time, the initial volume of the titrant, that was the initial volume of potassium manganate 7 used, was 22.60. Now the actual volume of potassium manganate 7 used was 11.30. So using this data, you expected to get that final volume of potassium manganate 7. Alright, as you've seen from the table of values, you are expected to complete that table. We are going to obtain the missing values. Are you getting me right? And then of course, as we know for all titration experiments, it's important that we determine the titer value. That is the average volume of the titrant, the average volume of potassium manganate 7 used. If it is purely an acid that we use as the titrant, we talk about obtaining the average volume of the acid used. So we are going to do this together. Now, after obtaining the average volume of the titrant, potassium manganate 7 used, we shall respond to the following questions. We'll do the analysis, of course. You are going to see how I analyze the questions. Question A, we are going to write the half-cell reaction equations. Remember, I told you that this titration experiment is redox titration reaction. And for being a redox reaction, reduction and oxidation are taking place simultaneously during the course of the experiment. So we need to know the half-cell reactions for oxidation and for reduction. Question B, we are going to write the overall redox reaction equation for this reaction. C, we will determine the molarity of A. Remember, A is our ammonium ion 2 sulfate crystals. Okay, we are going to determine the molarity of this substance, our analyte. Question D, we are going to determine the mass concentration of B. B here is the potassium manganate 7. So we'll get the mass concentration. The E part of the question, we are going to determine the number of moles of water of crystallization. And then finally, we are going to calculate the mass concentration of A. So these are the questions we are going to respond to after having obtained our titer value, our average volume of the titrant, average volume of potassium manganate 7 used. And quickly let me say this. From the hydrated crystal of ammonium ion 2 sulfate, the ion 2 ion there is serving as our reducing agent. In fact, that is the substance that is actually reacting with the potassium manganate 7 that we use as our titrant. Now, if ion 2 is serving as our reducing agent, it means that the ion 2 itself will be oxidized. Therefore, the reaction occurring to ion 2 is oxidation process. Then, potassium manganate 7 is serving as our oxidizing agent. It's serving as our what? Oxidizing agent. It is oxidizing that ion 2 ion. So if potassium manganate 7 is serving as the oxidizing agent, it itself will be reduced in the process. So what is happening to the potassium manganate 7 is reduction reaction. So we are going to write the half-cell reaction equation for these two. For ion 2 ion, which will be oxidized to ion 3 ion, and then we're going to write the half-cell reaction for potassium manganate 7, all right, which will be reduced from manganate 7 to manganate 2 ions. So let us first complete our table like I told you earlier. And so I'd like us to take a look at our table once again. Now you observe that in the first titration, the actual volume of the potassium manganate 7 used was not given. And so how do we get that? Please, you watch the table, you would see we have final volume of potassium manganate 7 used, we have initial volume of potassium manganate 7 used, and then the actual volume of potassium manganate 7 which we are to complete. We need to fill in that missing value. So what do we do? It's simple. Use the knowledge of subtraction. Are you following, right? To obtain that. Final volume minus initial volume would give us the actual volume of KMnO4 used. So if the final volume in the first titration is 11.50 and the initial volume is 0.00 cubic centimeter, then to obtain our actual volume of potassium manganate 7 used, it's going to be 11.50 minus 0.00, and that gives us 11.50. So in the first titration, the volume of potassium manganate 7 used is 11.50 cubic centimeter. Then we move on to the second titration. Now you observe from the table that the final volume of potassium manganate 7 used was 22.60. And now we were given the actual volume of potassium manganate 7 used as 11.10. We are required to obtain the initial volume of KMnO4 used during the Redox Titration experiment. So how do we obtain that? Remember once again, I told you final volume minus initial volume would give us actual volume of potassium manganate 7 used. And so if final minus initial would give us the actual volume, it simply means for us to get the initial volume, it is going to be final volume minus the actual volume of potassium manganate 7 used. It's just a knowledge of simple equation. Are you following, right? Collecting like terms. Because we have final volume minus initial volume equal to actual volume. So initial volume would now be final volume minus the actual volume of KMnO4 used. And so, using the values given to us, final volume 22.60, actual volume 11.10. So if we work on 22.60 minus 11.10, we are going to get 11.50 as the initial volume of potassium manganate used for the second experiment. Finally, the third titration. Now we are expected to obtain the final volume of KMnO4 used. We were given the initial volume to be 22.60. We were given the actual volume of potassium manganate used to be 11.30. So how do we obtain the final volume? Once again, recall, final volume minus initial volume is equal to actual volume. So if you're looking for final volume, once again, is an issue of making final volume subject to the formula. Of course, we are going to get the final volume is equal to initial volume plus actual volume of potassium manganate 7 used. So for the third titration, our final volume is going to be equal to 22.60, which is the initial volume, plus 11.30, which was the actual volume of KMnO4 obtained in the third titration. So if you add up these two values, 22.60 plus 11.30, this would give us 33.90 as the final volume of the KMnO4 used. Having completed the table, the next thing we have to obtain is the average volume of KMnO4 used. That's the average volume of our titrant. Is that okay? And the average volume of the acid, whereby we are titrating acid directly against the base, for example. This is also the same as the titer value. And it is also simply the same as the volume of the titrant used. In this case, the volume of potassium manganate 7. So how do we obtain this, the average volume? Simply go to the actual volumes. I following right in the table, and then add up the 3 actual volumes of potassium manganate 7 obtained. Once we add them up, we simply divide by 3 because we are looking for the average. Is that okay? And so this is going to give us 11.50 plus 11.10 plus 11.30 all over 3. Now we'll add up the numerators. We're going to get 33.90 divided by 3. And 33.90 divided by 3 gives us 11.30 cubic centimeter. So the average volume of the titrant, the average volume of potassium manganate 7 that was used in this Redox titration experiment, which actually reacted with our ammonium iron 2 sulfate, is 11.30 cubic cm. This we are going to use VB to represent because we are referring to our potassium manganate 7 as solution B, while our ammonium iron 2 sulfate, we are using A to represent that solution. So, from the average volume that was just calculated, our VB, the titer value, is going to be 11.30. And this we are going to use for the calculations. Good. Completing the table, very important, done. Calculating the average volume of the titrant used, very important, also obtained. It is now time we are going to move straight on to responding to the questions that were asked, all right, on this experiment. Before moving on into that, please let us take a look at the data given to us in this question. Okay, now from the instruction we're told that ammonium iron 2 sulfate is going to be referred to as solution A. So whenever you see me refer to A, know that we are talking about the analyte ammonium iron 2 sulfate. Is that okay? Now the mass of ammonium iron 2 sulfate given in the instruction was 3.34 grams. Okay, this was the mass of ammonium sulfate that was dissolved in 250 cubic centimeter of solution in order to obtain the mass concentration, of course, are you following, right, of this A, which is ammonium iron 2 sulfate. The volume of ammonium iron 2 sulfate used in this redox titration experiment was 25.0 cubic centimeter. This is actually the volume of the pipettes, all right? The volume of what? The pipette. You can take a look and then you see possibly written on it 25 cubic centimeter. Is that okay? So that's the volume of A. And then moving on, we have the next solution, the titrant, potassium manganate 7. All right, we refer to this solution as B. So once I make reference to B, please note that I'm talking about our titrant, okay, the solution in the burette, potassium tetraoxomanganate 7. In the instruction, the molar concentration of potassium manganate 7 was 0.015 mol per dm cube. This molar concentration of B is also the same as the molarity of B, or concentration of B in mol per dm cube. Then, of course, as obtained from the average volume of B used, that's the average volume of the titrant, the titer value, which is simply the volume of B, it is 11.30 cubic centimeter. Let us now move straight on to respond to the following questions as required in this titration experiment. The first, we are to write a balanced half-cell reaction equation for this redox titration reaction. And so how do we go about this? It's important for us to know that in any redox reaction process, there are these two processes that take place simultaneously. We have the reduction process and we have the oxidation process. And so we shall quickly take a look at the oxidation reaction in this titration experiment. Looking at the oxidation reaction, our interest is to get to know about the reducing agent. Because like I mentioned earlier, in the redox reaction process, the reducing agent will undergo oxidation. You get that right? The reducing agent reduces another substance. That another substance is called the oxidizing agent. What the oxidizing agent will do to the reducing agent is to oxidize the reducing agent. So what's the point? In a redox reaction process, the reducing agent is being oxidized. And because the reducing agent is being oxidized, the process occurring to that reducing agent is called oxidation. So the oxidation half-cell reaction equation will be what happens to our reducing agent. Like I told you earlier, the reducing agent is iron 2 ion. Iron 2 ion in solution A. In ammonium iron 2 sulfate, we undergo oxidation because it is the reducing agent. And now what happens in the oxidation process? Simply, the iron 2 will give up an electron, loses an electron because oxidation is a loss of electron, and then it is going to form iron 3. So take a look as you watch what is expected to happen in the oxidation process. So we have iron 2 ion as the reactant, okay? It is going to give us iron 3 ion. Then if you look at the reaction equation, you observe that it is not balanced. The oxidation number in the reactant part is 2. But in the product side, where iron 3 ion has been formed, we have the oxidation number to be 3. You know, when oxidation occurs, electron is being lost. The result is that the oxidation number will increase. I'm going to dedicate a special video lesson on redox reaction to give further explanation to this concept. Because believe me, all right, this is something you already have good knowledge of. Of course, when you talk about the fact that if an element loses an electron, it becomes a cation, positively charged. And so we consider that the oxidation number increases in the positive. And then when it gains electron, it becomes negatively charged. And so we can say that the oxidation number will decrease in the positive direction. Don't worry, like I said, a special video lesson is going to be dedicated to this explanation. For now, we are going to focus on what is required. Okay, like I said, the oxidation number of ion 2 will increase to ion 3 as you see showing on the screen. Now, the oxidation number of the reactant and product is not balanced. So we have to find a way to balance it. So what do we do? In the reactant, it is 2. In the product, the oxidation number of ion 3 is 3. So we have 2 to 3. We need to do a balancing. And how do we balance? Simply add electrons to the product side, to the ion 3. The reason is that electrons, they are negatively charged. So if you add it to any part of the reaction equation, what the electron you added would do is to reduce the oxidation number. Since the oxidation number in this case is plus, adding an electron to that ion 3 on the product side will reduce the oxidation number because you're going to have plus minus. And so the reaction equation goes in this form. Ion 2 ion in the reactant goes to product, giving us ion 3 ion after being oxidized. Okay, after the ion 2 ion is being oxidized, we get ion 3 ion, then plus 1 electron. Yes, 1 electron, because if you have 3 and you add minus 1 to it, remember electron is minus like I said. Okay, so adding 1 electron means you are adding 1 negative charge. So what is going to happen? You have on the product side now 3 plus or positive 3 for ion 3, then plus minus 1 electron. And so if you do 3 plus minus 1, you get plus 2. And so that the product oxidation number becomes plus 2, the reactant oxidation number for ion 2 also plus 2. And we can say that the oxidation half-cell reaction equation is balanced for now. We'll still come back and do something to it. But hey, don't worry. Hold on until we consider the reduction reaction equation. For now, know that the balanced oxidation half-cell reaction equation is ion 2 ion, the reactant, get oxidized, and then we get ion 3 ion in the product. Balancing it up, we have plus 1 electron, and then the equation is said to be balanced. Alright, let us now look at the reduction half-cell reaction equation. What are you expected to know about this? When dealing with the reduction reaction equation, it is the oxidizing agent that is being reduced. Alright? Now, in this Redox Titration reaction equation, what is our oxidizing agent? I mentioned that earlier. It is potassium tetraoxo manganate 7, KMnO4, solution B. That's the oxidizing agent. So this oxidizing agent is going to be reduced. Now, which species in it is going to be reduced? Which element? Manganate. Manganate. Now you have potassium tetraoxo manganate 7. The oxidation number of manganate in this compound is plus 7. So during the reduction process, it is going to be reduced to manganate 2. Alright? The ion 2, which is serving as the reducing agent, is going to reduce the manganate 7 to manganate what? 2 in the reduction process. So you get the point. As an oxidizing agent, the solution, potassium manganate 7, is going to be what? Reduced. The manganate 7 there will be reduced to manganate 2. So you see what happens. As an oxidizing agent, it undergoes reduction reaction. So you want to bear that in mind. I still want to repeat myself. Like I mentioned earlier, a special video is going to be dedicated to redox reaction equation. Alright, we are going to look at balancing this equation. I've shown you the general scheme of what happens to manganate in this reaction. Okay, from 7 to what? 2. A reduction. Let us balance the reaction and see. Now, remember generally that in the titration process, water usually forms. Okay? Water usually forms. And of course, because the MnO4 minus in the reactant has oxygen in it, to form the water, hydrogen needs to be introduced. And of course, don't forget that reduction reaction in terms of oxygen and hydrogen transfer is also defined as the introduction of hydrogen and removal of what? Oxygen. So because of the presence of oxygen in that oxidizing agent MnO4, which is undergoing reduction, hydrogen has to be introduced. Hydrogen ion. The work of the hydrogen, one, would be to react with the oxygen to give us water in the product. And two, to also help in balancing the oxidation number together with the electrons we're going to add. And so we have in the reactant now MnO4 minus plus H plus. That hydrogen is in ionic form, you know that. So it has the electronic charge plus 1, and then plus electron negative. Then in the product side, what are we going to get? The hydrogen in the reactant is going to react with the oxygen in the reactant, okay? And then it's going to give us water together with the Mn2 plus, that's the manganese 2 ion, which means that in the product we have manganese 2 ion plus water. Now we need to balance the atomicity in this reaction. The atomicity respecting hydrogen and then respecting oxygen. Are you following, right? Now you notice that in the reactant side we have 4 oxygens. And so in the product side we are expected to have 4 oxygens. And how do we achieve that? The water molecule, we attach 4 molecules to it. And if you attach 4 molecules to the water molecule in the product, you observe that the oxygen in the product will now become 4 atoms, which is the same as the 4 atoms of oxygen in the reactant in MnO4 minus. Then what about hydrogen? In the reactant, you notice that we have 1 atom of hydrogen ion. And then in the product, because of the addition of 4 molecules, the attachment of 4 molecules to water, hydrogen altogether becomes 4 times 2 in the product side, giving us what? 8 hydrogen atoms in the product. We will go to the reactant and then compensate for that. We have to get 8 atoms of hydrogen in the reactant. And to achieve this, simply attach 8 molecules to the hydrogen ion in the what? Reactant side. Okay? So that what we now have is MnO4 minus in the reactant plus 8H plus. Okay? Now if you consider the MnO4 minus and then plus that 8 hydrogen ion, the oxidation number of hydrogen in that 8 hydrogen ion is 8. And how do we obtain that? Simply the 8 molecules you attach times the oxidation number of hydrogen, which is 1 plus. If you work on 8 times 1, you would get plus 8. So you observe the oxidation number of hydrogen there is plus 8. Now the oxidation number of MnO4 minus, like I said, that radical together, its oxidation number is minus 1. You can see it showing there. And now if you have minus 1 oxidation number in MnO4 minus, and you have plus 8 oxidation number in hydrogen ion, that 8 plus minus 1, that is the 8 in hydrogen ion as oxidation number, plus minus 1 of the oxidation number of MnO4 minus. 8 plus minus 1 will give us plus 7. That's simply 8 plus, simply 8 minus 1. You get 7. So you notice that considering the MnO4 and the hydrogen ion, the oxidation number there will be 7. But if you take a look at the product side, the oxidation number we'll have there is 2 plus. That's plus 2, which is the oxidation number of manganese 2 ions. You notice the water molecule is a full compound, not an ion. For a full compound, the oxidation number is 0. So that 4H2O in the product side, its oxidation number is 0 already as a full compound, not an ion. If you add that oxidation number 0 to that of manganese 2 ion in the product, you have 0 plus 2. So in the product side, the overall oxidation number is 2. And then in the reactant side, the overall oxidation number, neglecting the electrons you are going to add, because electrons will not be the final thing we need to do to help us succeed. If you consider the hydrogen ion and the MnO4 minus, the oxidation number, as I explained already, is 8 minus 1, giving you 7. So you have reactant oxidation number 7 to product oxidation number 2. So you observe clearly that the oxidation number of the reactant is 5, greater than the oxidation number of the product side, 7 to 2. So what would we do in order to balance up the oxidation number? Remember, the atomicity has been balanced already. So we now have to find a way to now balance the oxidation number, the ionic charge. Remember, 7 to 2 in the reactant and product respectively. So to achieve the balancing is a simple thing. Alright? You go to where we have the higher number, higher oxidation number, which is the reactant side, 7. Then ask yourself, how many electrons will you add there so that it will balance up to give you 2 of the product? Remember, like I mentioned earlier, electrons reduces the overall oxidation number since electron is negative. So if you have positive and you are adding the electron, it will reduce. Okay? Plus minus reduces if you are doing addition. So if I have plus 7 and I want the plus 7 to reduce to plus 2 as you have in the product, what would you do to the plus 7? Is it not to subtract 5 from it? That's correct. So we are going to remove 5 from the oxidation number of the reactant. And to achieve this, simply add 5 electrons to the reactant side. On adding the 5 electrons to the reactant side, your problem is solved. So all in all, in the reduction half-cell reaction equation, the balanced reaction equation is now going to be MnO4 minus plus 8 hydrogen plus, that's 8 hydrogen ion, the plus there, then plus 5 electrons, 5e negative. If you work on the oxidation number in the reactant, then you see clear that it is 2. Because we are going to have minus 1 in the manganese ion part, alright, added to plus 8. Minus 1 plus 8 in the hydrogen ion will give us plus 7. Then plus 7 plus minus 5, which is in the electron part. 7 minus 5 gives us 2. And then in our product side, we still have our manganese 2 ion plus 4 molecules of water. And so we have balanced the reaction equation for the reduction reaction. The overall oxidation number on the product side is 2, the reactant side is also 2. So this is what we do in balancing the half-cell redox reaction equation for this redox titration experiment. And I hope you understood certain key points that I highlighted while explaining this half-cell redox reaction equation. At this point, we now are going to carry out what I consider as our overall balancing process for each half-cell reaction equation. The reason we are doing this is, I think the follow-up question, the big part of this question we are responding to, we actually require to obtain the overall redox reaction equation. So for us to avoid any challenge when we want to write the overall balanced redox reaction equation, there is something we need to do to these half-cell reaction equations. And what is that? We are going to balance up the electrons. Alright? We're going to balance up the electrons for the oxidation process and for the reduction process. So when we are writing the overall redox reaction, the electrons will cancel out because we don't need the electrons in the overall redox reaction equation, which we are going to respond to in question B of this titration question. So to achieve this, I am going to write out, watch as you observe on the screen, the oxidation half-cell reaction equation. We have iron 2 ion, which goes to product, giving us iron 3 ion plus 1 electron. Now what we are going to do is to multiply this oxidation reaction equation by 5. Why are we doing this? To compensate for the 5 electrons we added to the reduction reaction process. So what do I mean? Since in the reduction reaction process we added 5 electrons, we would come to the oxidation reaction process and then multiply the oxidation half-cell reaction equation by 5 That 5 is as a result of the 5 electrons we added to the reduction process. So that's just what you simply do. Which means that the main half cell oxidation reaction equation for this process will now be ion 2 ion giving us the product ion 3 ion plus 1 electron. Then of course I open something like a square bracket, and then I'll write times 5 there. Then we move on to the main reduction reaction process. Now remember that in the oxidation reaction we added 1 electron. So going back to our reduction reaction equation, that half cell reduction reaction equation will be multiplied by 1. That 1 is because of the 1 electron we added to the oxidation process. And so the main reduction half cell reaction equation for this titration experiment is now going to be MnO4 minus plus 8 hydrogen ion plus 5 electrons. Now to the product side, we have Mn2 plus, that's manganese 2 ion, plus 4 molecules of water. This reaction, we are going to multiply it by 1. So I have a square bracket there closing, then times 1. And so we are done formally with our half cell redox reaction equation for this redox titration experiment, both for the oxidation reaction and for the reduction reaction. Answering our A part of this question. Now, the second part of the question, that's the B part, we are asked to write the overall redox reaction equation. Write the overall redox reaction equation. So this is a simple process now. Once you are able to handle the half cell reaction equation, the overall becomes very simple, because all we have to do there is simply to combine what we have, all right, in the half cell reactions. We'll combine the oxidation reaction to the reduction reaction and then get our final product just exactly as we have them in the half cell reaction equation. So our overall redox reaction equation is going to be, are you ready? Good. We'll go to our original oxidation reaction equation, our oxidation half cell reaction equation. Remember that we have ion 2 ion in the reactant being oxidized to ion 3 ion in the product plus 1 electron added to balance up the oxidation number. And we said that you have to multiply that equation by 5, which means that the 5 will multiply each species in the reactant and in the product. So to write the overall reaction, we are going to pick what we have in the reactant part of the oxidation reaction. Remember, each term there is going to be multiplied by 5. So we have the equation, watch as it shows on the screen. 5 ion 2 ion. So I have picked the reactant part of the oxidation half cell reaction process. I will now move on to the reactant part of the reduction half cell reaction process and pick the reactant part also. Now remember that the reduction reaction, we said earlier that each species there is going to be multiplied by 1. If you're multiplying something by 1, there is no change. Are you following, right? So moving to the reactant part of our reduction half cell reaction equation, what we have there is MnO4 minus plus 8 hydrogen ion plus 5 electrons. So we're going to pick that and add it to the 5 ion 2 ion from the oxidation process. So what we are doing is simple. We are combining the reactant part of the oxidation and reduction half cell reactions. So this is what we have: 5 ion 2 ion plus MnO4 minus plus 8H plus, and then plus 5 electrons. Then going to the product side. Again, we're going to combine the product we obtained from the oxidation half cell reaction equation together with the product we obtained from the reduction half cell reaction process. And what do we have there from the half cell reaction equations? Now in the oxidation process we have ion 3 ion plus 1 electron. But remember we said that the oxidation reaction equation, the half cell of the oxidation process, We are meant to multiply each species by 5. So the ion 3 ion we have there is going to be multiplied by 5. And then of course the original 1 electron there is also going to be multiplied by 5. So that the product of the oxidation process, which we are now picking, will be, are you there? Good. Our overall reaction, the product side will now be 5 ion 3 ion plus 5 electrons. I have picked the product side of our oxidation half cell reaction. So I'm going to combine it with the product side of our reduction half cell reaction. And if you go to our reduction process, the product we obtain there, remember each of the species there is said to be multiplied by 1. Of course, there's going to be no change since you are multiplying the original reduction process by 1. Okay, so we go there and then pick the products of that reduction half cell reaction. And so what we have, the product there is manganese 2 ion and 4 molecules of water. So this is going to be plus manganese 2 ion, Mn2 plus, and then plus 4H2O. So this is the combination of the oxidation and the reduction half cell reaction equation which we obtained earlier. So you see, to obtain the overall redox reaction equation, you really need to do a great job from the half cell redox reaction equations, from the oxidation half cell reaction and reduction half cell reaction, because it's these two guys you're going to combine, reactant combine, product combine, to give you the overall redox reaction process. Okay, now with this, what do we have? You notice that in the reactant side, we have 5 electrons. And then in the product side, we also have 5 electrons. The 5 electrons will cancel out. So you notice that, and I told you when I was discussing how you handle and analyze the half cell reaction equations. If we had not done that cross multiplications, multiplying the oxidation process by 5 and multiplying the reduction process by 1, by the time we are carrying out this overall redox reaction balancing, we would have problems with our electrons. Is that okay? But you notice that because we've compensated for that in the half cell redox reaction equations, this balances directly on its own, naturally. So the 5 electrons, they cancel out, and then the overall redox reaction equation becomes, in the reactant side, 5 ion 2 ion plus MnO4 minus plus 8 hydrogen ion. And that gives us our product, 5 ion 3 ion plus Mn2 plus, that's manganese 2 ion, plus 4 molecules of water. Can you check the oxidation numbers of these guys and see that it balances in the reactant and in the product? Take a look at the reactant. What is the oxidation number in total? Looking at the ion 2 ion, you have 5 molecules of it. So it's going to be 5 times 2, giving you plus 10. I'm telling you the oxidation number now. Then in the MnO4 minus, the oxidation number of that whole radical is minus 1. So if you have 10 minus 1, you're going to get 9. Then move on to the 8 hydrogen ion. Multiply the 8 molecule by the oxidation number of hydrogen there, which is 1, you get 8. Then if you have your 9 originally, 9 plus that 8 would give you a total of 17 oxidation number in the what? Reactant side. Okay, that is 10 minus 1 plus 8. 10 minus 1 plus 8 gives us 9 plus 8, which is 17. So in the reactant part, the overall oxidation number in the overall redox reaction balanced equation is 17. Will this agree with the product? Take a look at the product and observe. In the ion 3 ion, we have 5 molecules there, so 5 times 3 would give us 15. That's in the product side. And then observe that we have manganese 2 ion. The oxidation number for that Mn there is 2 plus. 15 plus 2 will give you 17. Then 4 molecules of water. Water there is a full-blown compound, not an ion. The oxidation number of a compound is 0. So you're going to have 17 plus 0 as oxidation number in the product side, giving us 17. So of course we've done a wonderful work in the redox reaction equation balancing. This is absolutely great. Although, I had to take my time to explain this whole concept so that students that might have challenges with all this redox titration process and how to balance the ionic equation can get some good concept from it. Like I said, I would dedicate a special video lesson to redox reaction process because, of course, one can still encounter this when dealing with electrolysis and when dealing with electrochemical cells, and of course even electrolytic cell. Electrolytic cell, though, is discussed under electrolysis. So because of these topics in chemistry, I'm going to dedicate a special video lesson to redox reaction equation balancing. You wouldn't want to miss out in that video lesson. So please, if you've not subscribed to Jim's 41's YouTube channel, what is holding you? Quickly click the subscription button. Personalize your subscription by turning on the notification bell so that once I upload this content, you'll be personally notified. Now, from this final overall redox reaction balanced equation, we can pick the number of molecules of our solution A and the number of molecules of our solution B. Because you know, in titration reaction, it is always important for us to know what we call NA and NB. That's number of molecules of the species. Are you following, right? Number of molecules of the species. So our reducing agent, which is ion 2 ion, you observe from the overall balanced redox reaction equation that it is 5 molecules, all right? So Na will be 5. And then our oxidizing agent, MnO4 minus, the number of molecules which we're going to use Nb to represent is equal to 1. Which means that the mole ratio in which the reactant combined during the redox titration reaction process is actually 5:1. You know, we need that, especially because of the formula CAVA all over CBVB equal to NA over NB. Now, let us move on to question C of this titration experiment. We are asked to calculate the molarity of A, solution A. Remember, A is our ammonium ion 2 sulfate. Molarity of A. Molarity is the same as concentration of that species in mole per dm cube. It is also the same as the molar concentration. So we are calculating the molarity of A. And lest I forget, please, we also use Ca or Cb to represent the concept of molarity. So in this case, where we have to calculate the molarity of A, we shall also kind of refer to it as Ca. How do we go about obtaining the value of Ca? That is the molarity of solution A. We are going to quickly take a look at the data provided. Now you notice that we know the molarity of solution B, molarity of potassium manganate 7. So it's given in the question to be 0.015. Also remember that we know the volume of B. The volume of B, which is the average volume of potassium manganate used, the titrant, we obtained it to be 11.30 cubic centimeter. Also recall that we know the volume of A, the volume of our analyte, ammonium ion 2 sulfate. The volume is the volume of our pipette, which is 25 cubic centimeter. And from our overall balanced redox reaction equation, we have succeeded to obtain the mole ratio in which these two substances, solution, that were used in the titration experiment, the mole ratio in which they combine, A to B is 5:1. So because we know all of these data, the formula we are going to use in calculating the molarity of A, Ca, is going to be what we generally call the Cava formula. CAVA all over CBVB equal to NA all over NB. No wonder I had us obtain NA and NB, from question B. And so with this formula, CAVA all over CBVB equal to NA all over NB, we are looking for the molarity of A, which is Ca. Making Ca subject to the formula, we are going to get CBVB times Na all over Va times Nb. We can now substitute into this equation to calculate our molarity of A. Now substituting for this parameter in this formula, we are going to get Cb is 0.015. And so it's going to be multiplied by VB, which is 11.3, and then multiplied by NA, which is 5. All over VA is 25. We're going to multiply by NB, which is 1. Now, if we simplify the numerator, 0.015 times 11.30 times 5, and then we're going to get 0.875 divided by 25 times 1, which of course is 25. So how 0.8475 divided by 25, and then this gave 0.034. So the molarity of this solution A is 0.034 moles per dm cube. This is the molar concentration of solution A. This is the concentration of solution A in mole per dm cube. This is the same as the molarity of A, 0.034 moles per dm cube. The D part of the question, we are asked to calculate the mass concentration of B. Mass concentration of a substance is also the same as the concentration in grams per dm cube. Now being asked to calculate the mass concentration of B, we now have to quickly remind ourselves of the data, the information we know about B, potassium manganate 7. Now, since we know the full compound, potassium manganate 7, it means that we can easily get the molar mass of this compound. And good enough, from the question, the molar mass of the compound was given to be 158. Then we know the molar concentration of B. That is the molarity of B, the concentration of B in moles per dm cube, CB. We know the value. From the data provided, it's equal to 0.015 moles per dm cube. Now, if we know the molar concentration of B, and we know the molar mass of B, we can actually calculate the mass concentration of B using the formula molarity of B equal to mass concentration of B divided by molar mass of B. And now we are looking for the molar mass of B. We are going to substitute into the equation, or you can choose to cross multiply and make mass concentration of B subject to the formula first. So we have mass concentration of B equal to molar mass of B times molarity of B. Anyway, we might choose to substitute directly from the base equation, that is molar concentration of B equal to mass concentration of B divided by molar mass of B. The molar concentration of B is 0.015. That's going to be equal to mass concentration of B, which we do not know, all over molar mass of B, which is 158. So with this, we're going to cross multiply, where mass concentration of B will now be equal to 0.015 multiplied by 158. So if you multiply 0.015 times 158, we obtain that the mass concentration of B is 2.37 grams per dm cube. So the concentration of B in grams per dm cube, the mass concentration of B is 2.37 grams per dm cube. Now in the E part of the question, we are required to calculate the number of moles of water of crystallization in solution A. So how many moles is that water of crystallization? We use Y to represent it. We are going to find out how we obtain that. Now to obtain the number of moles of water of crystallization here, what we have to do ordinarily in getting the molar mass of a compound is simply to multiply the relative atomic mass of the elements present in that compound by their atomicities. Then we sum everything together and get the molar mass of that compound. But in this case of the ammonium ion 2 sulfate with some water of crystallization, it's not easy for us to get the molar mass at once because of that unknown Y in that compound. Alright, so what we're going to do here to get our number of moles of water of crystallization is to find another alternative way of obtaining the overall molar mass of this hydrated crystal. Okay, now if we know the molar mass, we will now come back and then carry out the multiplication of the relative atomic mass of the element by their atomicities and then add everything together, make it equal to the already obtained molar mass of this hydrated crystal. Then from there we can calculate the number of moles of water of crystallization. And how do we calculate it? Once again, we can rely on the formula molar concentration of A equal to mass concentration of A all over molar mass of A. Now you know already we have obtained the molar concentration of A. We calculated the molar concentration of A to be 0.034 moles per dm³. Our problem here is to get the molar mass of solution A. Now, what is the mass concentration of A? It was not directly given to us in the question. However, there were data provided that we can use in obtaining the mass concentration of A so that we can substitute it into this formula and then calculate our molar mass of A. Did you take note that in the instruction we were told that the mass of A, which was dissolved in a given volume of solution, was 3.34 grams. This 3.34 grams of A was dissolved in 250 centimeter cube of solution. Now from that information we can calculate the mass concentration of solution A. And how do we do that? Generally, the mass concentration of a substance, if you know the mass of that substance and the volume in which that mass was dissolved, we can obtain the mass concentration to be the mass of the substance divided by the volume of solution. If the volume of solution is given in cm³, then that formula mass over volume will be multiplied by 1000. And that is what we are going to do here to get our mass concentration. Okay? Because we need this mass concentration to substitute in that formula molar concentration of A equal to mass concentration of A divided by molar mass, so that we can calculate the molar mass of A. So going by that, our mass concentration from the information provided in the instruction is going to be 3.34 all over 250 times 1000. And if we do this, 3.34 over 250 times 1000, we get the mass concentration of solution A as 13.36 grams per dm³. So the mass concentration of A is 13.36 grams per dm³. So we can now smile. All we have to do is go back to our equation, our formula. The molar concentration of A is 0.034 equal to mass concentration of A, which is 13.36, all over molar mass of A, which we do not know. Cross multiplying and of course making molar mass of A subject to the formula, we are going to have molar mass of A equal to 13.36 divided by 0.034. And of course, if you work out 13.36 divided by 0.034, this gives us that the molar mass of solution A, 392.9 grams per mole. Is that okay? So the molar mass of A is 392.9 grams per mole. Having obtained this molar mass, all we now have to do is to go back to the compound solution A. We are going to obtain the molar mass in the usual way by multiplying the relative atomic mass of each element by its atomicity. Then we'll add up everything we have there, make it equal to 392.9. Then from there we can solve for the number of molecules of water of crystallization. Please, can we do this? Our solution A is ammonium iron 2 sulfate. The hydrated form written in full form is FeSO4 open bracket NH4 close bracket then 2 SO4 YH2O. That is the compound solution A, hydrated form of ammonium iron 2 sulfate used in this Redox titration reaction. Alright, so what we're now going to do, we have the relative atomic mass of each element that makes up this compound. It was provided in the instruction. And so we have iron, which is Fe, the relative atomic mass is 56, plus sulfur, relative atomic mass is 32, plus oxygen. The relative atomic mass of oxygen in that FeSO4, the relative atomic mass of oxygen is 16. The atomicity of oxygen there is 4, so it's going to be 16 times 4. So let us get that part of FeSO4. Now in the compound we still have NH4 and then enclosed in brackets 2 atoms outside. Now nitrogen, the relative atomic mass of nitrogen is 14. So we're going to add it to that of hydrogen there. Hydrogen is 4 atoms in NH4. So the relative atomic mass of hydrogen is 1. It's going to be 1 times 4. We shall multiply this 14 plus 1 times 4. We'll multiply it by 2 because the NH4 altogether is 2 atoms, as you can see in that NH4 in bracket and then subscript 2. Okay, then let us move on further. We have SO4 attached to that NH4 too, okay? S there is 32 relative atomic mass, and then oxygen, the relative atomic mass is 16. We are going to multiply it by 4. So we have obtained that part, NH4 in bracket 2, SO4. Alright, what it gives to us is 14 plus 1 times 4 in bracket times 2 plus 32 plus 16 times 4. So we now take a look at the water of crystallization part. We have YH2O. Now the relative atomic mass of hydrogen is 1. We're going to multiply it by 2. Then plus O there. Oxygen, the relative atomic mass is 16. Okay? But then take note that we have Y molecules there. So if we have 1 times 2 plus 16, altogether there is going to be multiplied by Y, which is the number of moles of water of crystallization. So with this addition being done, we are going to equate everything. It is expected that this, addition, this summation of the product of the relative atomic mass by their atomicities is going to be equal to the molar mass of A. And of course, the molar mass of A we obtained already to be 392.9. So we make this whole summation equal to 392.9. Simplifying the left-hand side further, we are going to get 152, which of course is the summation of 56 plus 32 plus 16 times 4. And then added to 132, which is the summation of the part 14 plus 1 times 4 times 2, then plus 32 plus 16 times 4. That ammonium sulfate part. Then added to the water molecule part, 1 times 2 added to 16 is going to give us 18, multiplied by Y, our number of molecules of water of crystallization. Doing this, we equate to 392.9. So if you add up 152 plus 132, we arrive at 284 plus 18Y. That 284, by collecting like term, is going to be subtracted from 392.9. If you do that subtraction, we are going to get 108.9. So 18Y is equal to 108.9. And then to get our Y, the number of molecules of water of crystallization, we shall divide through by 18. 108.9 divided by 18 gives us 6.05. If you approximate this, because of course your number of molecules of water of crystallization is expected to be in whole number. So 6.05 approximated to the nearest whole number is going to give us 6. So Y there in solution A, which is the number of moles of water of crystallization, is 6. With these, we can write solution A fully now to be FeSO4, open bracket, NH4, close bracket, 2, and then SO4. Then we have 6H2O. And of course, this is ammonium iron 2 sulfate hexahydrate. Once again, ammonium iron 2 sulfate hexahydrate. This is also called the Mohr salt. The Mohr salt. M-O-R-H. Salt. That's the name of this salt. Take note. In case you hear of Mohr salt. Just like you have of washing soda, you hear of gypsum and the rest of them. This ammonium iron 2 tetraoxosulfate 6 hexahydrate is called the Mohr salt. Okay, friends, we've done a lot of great jobs here. We are going to conclude this whole titration experiment stuff by looking at the last part of the question, question F, where we are asked to calculate the mass concentration of A. And of course, this I have already obtained along the line. Remember, I think that's in E part of the question, to get our number of molecules of water of crystallization, we did something where we had to get the mass concentration of A first, because we needed that to solve the molar mass of A. And of course, that has not changed. It's the same thing we do in the F part of this question where we were asked to calculate the mass concentration of A. So straight on, we are going to proceed to calculate the mass concentration of A. Alright? The mass of A given to us was 3.34 grams. This mass was dissolved in 250 cubic centimeter of solution. And so like I stated earlier, under part E of this question, the mass concentration will be equal to the given mass divided by the volume of solution. Because the volume of solution is given in cubic centimeter, we are going to multiply that by 1000 to convert to cubic decimeter, that is dm³. So doing this straight on, we have mass concentration of A, which is the same as concentration of A in grams per dm³, equal to 3.34 divided by 250. Multiply that by 1000. So if you divide 3.34 over 250, obtain a value and multiply by 1000, we get 13.36 as before, as the mass concentration of A in the unit grams per dm³. Alright friends, this is how we carry out the analysis of redox titration experiment work. I hope you enjoyed the way I handled this calculation and explanation step by step. I'm confident that this video lesson is going to guide you in handling any other aspect of redox titration problems. Please do kindly subscribe to my YouTube channel if you've not already done so. Turn on the notification bell and personalize the subscription so that once I upload any new content, you will be personally notified. And please like and share this video. Make it viral so that so many other scholars will get access to it and benefit from it. Someone who is preparing for Waec would need this video a lot because of course titration is part of their examination work. NECO, GCE, mention them. If you are in higher institution, you also need to watch this video lesson. So please guys, help me and share this video lesson so that as many as possible will encounter it and learn something good from it. I hope to see you in my next video lesson. However, if you have any question, please feel free to make use of the comment section and I'll be right there to respond to your question. I hope to see you next time. Until then, please have fun with your studies, alright? And do enjoy your time.